Climate change in cities is one aspect of measuring sustainability in cities. We measure climate change effects in terms of greenhouse gas emissions, or GHGs. Let's put cities in global context first and then dive into the greenhouse gas emission specifics. So far, population growth has been driving growth in cities, where cities are home to over 50% of the world's population and expected to rise to 70% by 2050, according to the United Nations. Activities of these urban populations consume fossil fuel-based energy, where the International Energy Agency shows that in 2012, the world saw a near doubling of the energy demand since 1980, and this demand is expected to rise another 85% by 2050. As a result of fossil fuel use in cities, greenhouse gas emissions account for 70% of global emissions, and this is expected to increase to 76% by 2030 at current trends of urbanization and economic growth, which is a statistic by ICLEI, Local Governments for Sustainability. Climate change is measured as a global warming potential, which is expressed in terms of greenhouse gas emissions and are measured in units of tons of carbon dioxide, CO2. To get a sense of size for these units, take a look at this image. This cube was created as an art installation at the 2009 Copenhagen Conference for the United Nations Framework Convention on Climate Change, the UNFCCC. It was created to give conference participants a visual of what 1 ton of CO2 looks like, and was created by building a 3-story tall cube made from shipping containers and had 2 sides draped with screens to project images and videos. This cube measures 27 feet on all sides, that is, it measures almost 8 meters by 8 meters by 8 meters. From research by Kennedy and colleagues looking at 10 global cities, we'll take a look at the findings of greenhouse gas emissions from these 10 cities, which are Los Angeles County, Greater Toronto Area, Geneva Canton, Greater Prague, Cape Town, Denver City and County, New York City, Greater London, Barcelona, and Bangkok. So why does it matter? It's because cities are key drivers of greenhouse gas emissions, but some are more knowledgeable or perhaps more creative or have access to resources to work on reducing these emissions. Quantifying these emissions is the first step towards finding solutions to reducing them. The greenhouse gas emissions that are quantified in greenhouse gas emissions inventories are determined for 7 components, which include electricity, heating and industrial fuels, industrial processes, ground transportation, aviation, marine, and waste. Notice that energy consumption is generally accounted for here by fuel type rather than by sector. For purposes of the urban inventories identified in the research by Kennedy et al., we'll look at the 5 categories highlighted in red, which exclude industrial processes and marine from the 7 components. Throughout the findings that will be demonstrated next, you will notice that the greenhouse gas emissions attributable to cities are a balance between 2 things: geophysical factors and technical factors. The geophysical factors include things like the city's climate, warm or cold, access to resources, like access to solar or access to hydropower, and gateway status, that is to say, for example, is it a port city or a landlocked city, does it have an airport, etc. Technical factors include things like the technologies or strategies for power generation, urban design, and waste processing as examples. Taking a look at the greenhouse gas emissions from the inventory list identified earlier, we'll start with electricity. I might refer to greenhouse gas as simply GHG from time to time. GHG emissions resulting from electricity depend on the amount of electricity consumed and the GHG intensity of the supply. The intensity of the power supply is an indication of the sources of fuels that go into the generation of this electricity supply. It's a measure of the cleanliness of the electricity, if you will. The chart here shows a bar graph where the x-axis is the consumption in terms of megawatt hours per capita, and the consumption is plotted for each of the 10 cities aligned on the y-axis. 7 of the 10 cities have an electricity consumption that is within a range of 4.5 to 7 megawatt hours per capita. This electricity consumption is for all types of electricity uses, also known as end uses, and include end uses in residential, commercial, industrial, and transportation, but excluding that from combined heat and power plants in the city. Of the remaining 3 cities, Denver's consumption comes out to 11.49 megawatt hours per capita, and Toronto is at 10.04 megawatt hours per capita, which means they have substantially higher per capita consumption. Cape Town has the lowest at 3.49 megawatt hours per capita, where a possible explanation could be due to the lower average household income, which results in lower electricity consumption. A possible explanation for the higher consumption in Denver and Toronto may be due to high commercial and industrial contributions, as well as their climate. Considering residential electricity use only in Denver and Toronto, this use represents 34% and 21% of the total electricity used, respectively. A more important factor of GHG emissions from electricity is the GHG intensity, also referred to as the emissions factor of the supply mix. This chart here is a bar graph, like the previous one, showing the GHG intensity of the electricity supply on the x-axis, measured in tons of CO2 equivalent, denoted as TECO2 per gigawatt hour. The 10 cities are listed on the y-axis. The GHG emissions attributable to electricity consumption for the 10 cities display a wide range. It's always interesting to look at the longest bar and the shortest bar and try to understand possible explanations behind these large and small values. The longest bar is Cape Town's. With 92% of South Africa's electricity generated from combustion of coal, Cape Town has the highest GHG intensity at 969 tons of CO2 equivalent per gigawatt hour. The shortest bar is Geneva's. Geneva's supply mix is based primarily on hydropower and has an intensity of just 54 tons of CO2 equivalent per gigawatt hour, including line losses. Actually, Geneva might be considered to have almost zero emissions from electricity, since it exports hydropower but has small emissions from the purchase of electricity from a combined cycle natural gas generating facility in Luxembourg. Toronto's GHG intensity is considered on the low end, together with Barcelona. Observations from the two charts show that Toronto's high consumption is offset by its low GHG intensity, while the opposite is true for Cape Town, where its low consumption is mediated by high GHG intensity. Putting the two charts together and adding a third axis, this chart is produced. It shows on the x-axis the electricity consumption in megawatt hours per capita from the first chart and goes from 0 to 1,000. The emissions factor, or GHG intensity, representing these wedges on the chart, measured in tons of CO2 equivalent per gigawatt hour, is on the y-axis on the right, which is from the second chart. And the new addition is the y-axis on the left, which is the electricity emissions measured in tons of CO2 equivalent per capita. This axis shows that emissions from 7 of the 10 cities fall within the narrow range of 2.46 to 3.38 tons of CO2 equivalent per capita. On a per capita basis, the lowest electricity emissions are those for Geneva at 0.35 tons of CO2 equivalent per capita, which is a factor of 26 less than Denver, primarily because Geneva has access to hydropower. Again, to compare Toronto and Cape Town, you can see that Cape Town has the lowest consumption because it appears to the right on the x-axis, but has the dirtiest electricity, meaning it's in the top wedge, representing a high emission factor, or as we also refer to it as GHG intensity of the electricity supply. Toronto, on the other hand, has one of the highest consumptions, as it appears on the far left of the x-axis, but relatively clean emission factor, and appears in the wedges towards the bottom. Some cities rely on their national, state, or provincial grids for their power supply, while other cities have some control and more autonomy over their local supply, or they purchase electricity on international markets. Moving on to heating and industrial fuels. The consumption of fuels for heating and electricity, that is, the stationary combustion in all sectors, excluding electricity because it is captured separately, corresponds quite closely to the heating degree days, using an 18 degrees Celsius as a base temperature. The graph here shows the heating degree days on the x-axis. Degree days are a combination of time and temperature, and so heating degree days are the number of days in which the temperature falls below the base temperature times that temperature differential, which requires people to turn on their heating. On the y-axis, there's energy consumption measured as gigajoules per capita. The cities are plotted, and the linear fit is also shown on the graph. On the high end, Denver and Toronto have the greatest consumption at 73.5 and 58.9 gigajoules per capita, respectively, while on the low end, Cape Town and Barcelona each consumes less than 16 gigajoules per capita. Of the American cities, New York, Los Angeles, and Denver, all three cities lie above the best fit line, possibly due to larger house sizes or building characteristics. Notice, also Bangkok is above the best fit line, primarily due to high fuel consumption for industrial processes, because in terms of heating alone, Bangkok sits at 0 heating degree days. In Bangkok, only 5% of this consumption is for residential use. While heating degree days can explain the differences in energy consumption among cities, there is some variability associated with the types of industrial fuels used, technical factors pertaining to building characteristics, such as the quality of the building envelope, and socioeconomic factors, such as the price of energy. The GHG emissions from heating and industrial fuels correlate with energy consumption, though the main exception is Prague, which gets 15% of its heating directly from coal, and an additional 17% from a heat pipe powered by coal. So while Prague uses less heating fuel energy in comparison to New York City on a per capita basis, it jumps above in terms of emissions per capita due to the higher emissions intensity of coal. Similarly, Cape Town and Geneva also have slightly elevated emissions due to their predominant use of oil heating, relative to the other cities that primarily use natural gas. Industrial emissions considered so far are only those associated with energy end uses. Direct industrial emissions from industrial processes were determined for Los Angeles, Prague, and Toronto as they pertain to cement manufacture. Turning our attention now to ground transportation. Ground transportation emissions are determined for combustion by vehicles within the city boundaries, excluding electrical forms of transportation. This graph here shows population density on the x-axis measured in persons per square kilometers, and transportation emissions, or GHGs, on the y-axis, measured as tons of CO2 equivalent per capita. The cities are plotted on the chart, and the best fit line is superimposed. An inverse relationship can be seen between urban transportation energy use and population density. Since GHG emissions from ground transportation are dependent on the use of fossil fuels, conclusions regarding the dependence of transportation energy on urban density hold true for GHG emissions. The best fit line shows that a doubling of intensity from 2,500 to 5,000 persons per square kilometer corresponds with a 40% decrease in GHG emissions. Of the three American cities, two of them, that is Denver and Los Angeles, have significantly higher GHG emissions than the other cities. New York City is different. Denver's per capita emissions from ground transportation fuels is 6.31 tons of CO2 equivalent, which is 8 times higher than those of Barcelona at 0.77 tons of CO2 equivalent. In the long run, over several decades, the North American cities might ideally reduce per capita emissions by pursuing smart growth policies that increase population density while at the same time improving the design and variety of transportation options. The GHG emissions were calculated based on fuel sales data, vehicle kilometers traveled, or by scaling from a regional level data. These three approaches were found to differ by less than 5%. When looking at cities with similar densities, there is a variation in GHG emissions between cities of similar densities. So, locate Toronto and Denver on the graph. Both have comparable densities. Denver's ground transportation emissions are actually 2.26 tons of CO2 equivalent per capita higher than those of Toronto. Now locate Geneva and London on the graph. You can see comparable densities again. In terms of GHG emissions, though, Geneva's is 0.63 tons of CO2 equivalent per capita, which is higher than those for London. Some of this variation may be due to differences in vehicle fuel economy and the extent of car use, which is a reflection of the quality of public transit, land use planning, and government policy regarding transportation. Air and marine GHG emissions are generally reflective of a city's gateway status, that is, its access. Here's a chart of aviation emissions. On the x-axis, there's jet fuel loaded at major airports in megaliters, and on the y-axis, there's the 10 cities. Emissions from air travel go beyond the activities in the cities and include travel between urban centers that happens on a global scale. The calculated emissions are those from combustion of fuels loaded onto the airplanes at the city's airports. Only airports within the city boundaries are included. So, for example, aviation emissions from London would include Heathrow and City Airport, but would not include Gatwick and Stansted. It is possible that GHG emissions determined for the other cities exceed those that could be attributable to residents of the cities, as the airports also serve wider regions beyond city boundaries and involve connecting passengers. The gateway status of a city contributes to its economy by providing jobs and contributing to agglomeration effects. The same applies to marine travel and would include the fuels loaded on ships at marinas, but we've only shown aviation emissions here. And now waste emissions. Waste emissions are the methane emissions from landfill waste, and then converted into the same units we've seen earlier into tons of CO2 equivalents. In this chart, we have the GHG emissions from waste on the x-axis in units of tons of CO2 equivalent per capita, and on the y-axis, the 10 cities. The emissions are calculated based on a total yield gas approach, like the approach recommended by the Intergovernmental Panel on Climate Change, IPCC, where the degradable organic content is an important variable. This variable indicates the amount of carbon in waste that is disposed of, and that is responsible for the methane released. If cities have good data on their waste, a first-order decay approach is preferable. Generally speaking, for most cities, the degradable organic content is around 0.2 tons of carbon per ton of waste. There are exceptions, however. London's is slightly less because a large fraction of waste is construction waste, and Cape Town's is slightly more because there's a high content of waste paper. At the landfills, the way in which methane is captured or recovered plays a significant role in the total methane released from waste. From the chart, you'll see Cape Town and Bangkok have the largest values for waste emissions, both above 1 ton CO2 equivalent per capita, because they have no methane capture. The methane recovery factor is about 75% in the other 8 cities, which, as expected, brings waste emissions below 1 and even below 0.5 tons of CO2 equivalent per capita. There's a lot of uncertainty around the levels of methane recovery that is achieved, and other debates around landfills capturing the carbon that would otherwise be released. The contribution of waste is part of the uncertainty in a city's GHG inventory, though keeping in mind waste is a minor contributor to the emissions from most cities, as you can tell by the small values of these numbers. Which brings us to the total emissions. The chart here shows the GHG emissions in tons of CO2 equivalent per capita on the x-axis, and the y-axis shows the 10 cities. The bars on the chart show emissions within the city in yellow, direct emissions in green, and life cycle emissions in red. The total end-use emissions for the 10 cities range between 4.2 and 21.5 tons of CO2 equivalent per capita. Barcelona has the lowest per capita emissions due to its high population density, low heating requirements, and relatively clean electricity. On the contrary, Denver has the highest per capita emissions, mainly due to electricity, heating and industrial fuels, and ground transportation. The next 2 highest emitters are also both North American, Los Angeles at 13 tons of CO2 per capita and Toronto at 11.6 tons of CO2 equivalent per capita. The other cities all have emissions fairly close to 10, though Geneva is less than that at 7.8 tons of CO2 equivalent per capita. These values for end-use emissions are typical of those reported by municipal governments. In other words, these are the yellow bars on the chart representing emissions within city boundaries and can be seen reported for 5 cities only. The actual emissions that occur within city boundaries are lower than the emissions that are actually attributable to end use in cities. In most cases, the GHG emissions associated with electricity use in cities occur outside, where more often the generation of this electricity happens outside of city boundaries. For example, in Prague, a heat pipe provides 17% of the city's heating requirements, with the GHG emissions from the combustion of coal occurring many kilometers away. The main exception is Barcelona, which has natural gas power plants within its borders, as well as its imports of fuel. The GHG emissions from landfill waste also occur outside of city boundaries, in some cases, where waste is disposed of outside of the city. It is therefore appropriate to attribute to cities to more than just the emissions within city boundaries, as the consumption activities located in the cities result in emissions elsewhere. The electricity generation emissions that happen outside the city but are consumed in the city are the direct emissions represented by the green bars in the chart, and have been determined for all 10 cities. Emissions within city boundaries were found to range between 45% and 95% of direct emissions. If emissions are to be attributed to cities based on consumption activities, however, then a fuller life cycle perspective should be considered. Beyond the GHGs emitted during the combustion of fossil fuels, for example, there are emissions produced from the extraction, processing, and transportation of these fuels to cities. The life cycle emissions are between 7% and 24% higher than the direct emissions for the cities, and can be seen in the red bars on the chart reported for 8 cities. The greatest changes in life cycle emissions are observed for the North American cities, since they have higher life cycle emissions. The different types of emissions and the different scales of emissions, particularly the life cycle and upstream emissions, show that GHG emissions attributable to cities are in reality higher than we recognize. As Kennedy et al. Conclude, the understanding that this GHG analysis among 10 cities provides is beneficial as cities seek to reduce emissions by learning from the best practices of others. This comparison among cities suggests that cities may learn best from cities with similar geophysical environments. For example, with a warm Mediterranean climate and a dense urban form, Barcelona has the lowest emissions of the 10 cities, which means a high-emitting city like Denver, on the other hand, might learn more by comparing its metabolism with Toronto, which has a more similar climate and is closer in terms of population density than Barcelona. We can identify other possible partners among these cities. For example, London and New York have similar densities and climates, so they should be comparing each other's building codes and other policies to attract alternative energy technologies and sustainable transportation. Other aspects can be learned from this analysis. For example, it could be concluded that reducing electricity demand in Geneva, which has relatively clean electricity anyway, would be a waste of resources. But reducing electricity demand in Cape Town, Denver, or Prague, which have high intensities to begin with, could result in substantial reductions in emissions. For cities such as Denver, Los Angeles, and Toronto, their low population density creates challenges across the urban sectors. These relatively newer cities would need to grow to support smart growth with the multiple objectives of regional accessibility to jobs, population density, design in terms of multimodal transportation design, and diversity of land.